Hello everyone! This video is entitled Writing and Naming Covalent Compounds. In this lecture, I will provide the framework for writing out the chemical formulas of covalent compounds from their given names, and outline the procedure for naming covalent compounds displayed to you as a chemical formula. If you have not yet watched my video on covalent bonding, it is recommended that you do so first to fully understand this material. You can find a link to that video in the description below. Okay, let's get started.
Covalent compounds, as we know, are composed of bonds usually between two or more nonmetals. These nonmetals share their electrons until they satisfy the octet rule and become stable. However, it is important to remember that it's possible for certain metals to form covalent bonds with nonmetals as long as the difference in electronegativity between the two bonding elements is equal to or less than 1.6. So, to identify compounds as either ionic or covalent, you must consider two things. One, whether charged ions are bonding. And two, if the difference in electronegativity between the bonding elements is above or below 1.7. Remember that 1.7 is the threshold. 1.7 and above is an ionic compound. Less than 1.7 is a covalent compound. So we have four compounds listed below. Let's take a closer look at each one of them and see if we can identify ionic from covalent. The first compound we have is composed of aluminum and bromine. You always need to identify the metal and the nonmetal first before you can identify this compound as being either ionic or covalent. And so we know that aluminum is of course a metal and bromine is a nonmetal. Now at first glance, you're thinking, oh, this must be an ionic compound. It's composed of a metal and a nonmetal. But in fact, if you were to take the difference in electronegativity between these two elements, you'd find that the difference is actually less than 1.7, making this compound covalent. So instead of this compound being named aluminum bromide, its covalent name would be aluminum tribromide, and that is the only correct name for this compound. But more on that later. The next compound we have is composed of sodium and nitrate. So to start, you need to identify the metal and the nonmetal. So we know that sodium is the metal and that nitrate is the nonmetal component. Now you may be thinking, let's take the difference in electronegativity. Well, you need to remember that the difference in electronegativity is only helpful when determining if a binary compound, that is a compound with two different elements, is ionic or covalent, or if a particular bond within a compound is ionic or covalent. But when we have more than two different elements in a compound, such as this one that has three elements, it's very difficult to determine using the difference in electronegativity if the compound is ionic or covalent. So let's just re-examine what we already know about this compound. We know that it's made out of metal and nonmetal, and we know that it's composed of two different ions, the sodium ion and the nitrate ion, which firmly places this compound in the realm of ionic compounds. Now, even though this compound contains nonmetal components, remember, the nitrate compound is a compound that's charged. Even though that's covalent, it's bonded to a metal as an ion, which makes the entire compound as a whole ionic. Our third compound is composed of carbon and oxygen. So again, to start, we need to identify metal and nonmetal. We know that carbon is a nonmetal, and we also know that oxygen is a nonmetal. And so these two nonmetals obviously will form a covalent compound. For our last example, we have a compound composed of carbon and hydrogen. And so, as always, we need to first identify any metals and nonmetals. So we know that carbon is a nonmetal, which brings us to hydrogen. Hydrogen is officially classified as a non-metal. However, there is quite a bit of debate surrounding its classification. This is because hydrogen is in fact capable of acting as a metal when it forms bonds with certain types of elements. And so it is this duplicity that has the scientific community somewhat confused about hydrogen. Is hydrogen a nonmetal because it is capable of forming bonds as a nonmetal, or is it a metal because it can act as a metal in certain compounds? What really pushed this question forward, in fact, was data collected by the Galileo probe that was sent to investigate Jupiter and its moons. The data showed that Jupiter has a massive ocean underneath its very thick atmosphere that surrounds the entire planet. This ocean is made entirely of liquid metallic hydrogen. And so this has led scientists to believe that maybe we've misclassified hydrogen because we cannot study the element under the certain temperatures and pressures that would cause it to exhibit true metallic properties. And of course, this also substantiates why the element is located on the metal side of the periodic table. Anyways, although this is a very interesting debate, how exactly is it relevant to determining if a compound is ionic or covalent that contains hydrogen? Well, in fact, chemists have established a general rule for writing hydrogen in a chemical formula to enable a reader to quickly determine if hydrogen is functioning as a metal or as a nonmetal within the compound. If hydrogen is written at the end of the chemical formula, as shown in this compound, then it is functioning as a nonmetal. But if hydrogen is written at the start of a chemical formula, then it is usually considered to be functioning as a metal. Of course, the main exception to this general rule would be water, written as H2O. But of course, we know that hydrogen in water is a nonmetal. And so going back to this example, with the information that we have at hand, we know that this compound is a covalent compound because the hydrogen appears at the end of the chemical formula and is functioning as a nonmetal. And with that, we arrive to the naming covalent compound section of this package. You need to keep in mind that the crossover rule that is used to write ionic compounds is never used for covalent compounds. The chemical formula of ionic compounds is the product of crossing over the charges of opposing ions and then simplifying those charges to the lowest possible ratio. When it comes to covalent compounds, you cannot simplify the subscripts in the chemical formula. And those chemical formulas are not the byproduct of the crossover rule. Remember, the rule is exclusive to ionic compounds. And so, how do we write out the subscripts of covalent compounds? And how do we name those compounds based off of their subscripts? Because of course, each one of those numbers is incredibly important in telling us something about that compound. Well, when writing covalent bonds, Greek prefixes are used to show the number of each type of atom in the chemical formula. And of course, remember that the second element has the ending "ide." And so the prefixes that are used to represent the numbers 1 through 10 are called mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Now, the only prefix that is not used as often as the rest is mono. If there's only one atom of an element within a compound, the prefix mono is omitted in most cases. There are one or two exceptions to this rule, such as carbon monoxide, but for the most part, the prefix mono is not used. And so let's take a look at some examples together to really solidify this concept. For our first example, we have a compound composed of carbon and fluorine. Of course, when naming covalent compounds, there are steps. There are 4 steps. The first is to identify the metal and nonmetal in the compound, and then check the difference in electronegativity. It just so happens that both bonding elements in this compound are nonmetals. And so I'm not really interested in determining the difference in electronegativity here, because that's only relevant when one of the elements is a metal. If both of them are nonmetals, I know that the compound is covalent, and so I can continue naming this compound covalently. The second step is to write out the element names. And so I know one will be carbon and the other will be fluoride. The ending must be "ide" because it's the second element. And the third rule is to count out how many of each element I have. And so I know I have 1 carbon and I have 4 fluorines. And finally, place the prefix that corresponds to the number in front of the name of the element. And so because I can omit mono, the only prefix I really need to place into this name is tetra. And so this compound will be called carbon tetrafluoride. For our second example, we have a compound composed of nitrogen and fluorine. For the first step, I need to identify any metals or nonmetals I have in the compound, and then check the difference in electronegativity. But again, I have a compound that is entirely composed of nonmetals. So I know that this compound will be covalent, and I can continue naming it in a covalent fashion. The second step, write out the element names. So nitrogen, fluoride. Remember, the ending must be "ide" for any element that comes second. Third, count how many of each element you have. So I know I have 2 nitrogen and 2 fluorine. The last step, place the prefix that corresponds with the number in front of the name of each element. I know that 2 in Greek prefixes is di. And so at the start of each one of these elements, I'm going to place di. Dinitrogen, difluoride. For our last example, we have a compound composed of phosphorus and chlorine. First step, identify any metals or nonmetals present in the compound, and then check the difference in electronegativity. Again, both are nonmetals, so I know it's a covalent compound, and I'm going to continue naming it covalently. Second step, write out the element names. So I have phosphorus, chloride. Third step, count how many of each element you have. I have 1 phosphorus, and I have 5 chlorine. Step 4, place the prefix that corresponds with the number in front of the name of the element. Remember, for 1, I have the prefix mono, which I can omit. And for 5, I have the prefix penta. So I'm going to place penta in front of chlorine, and I now have phosphorus pentachloride. Okay, so here, you must take note of a very important restriction that scientists have placed on the naming of covalent compounds. When using Greek prefixes, 2 vowels cannot be adjacent to one another. The A or the O at the end of a prefix must be dropped when it precedes a vowel in the name of a compound. However, the I at the end of the prefixes di and tri are never dropped. Okay, so what does this look like in examples? Well, the 2 compounds we have here are composed of nitrogen and oxygen. The first is called dinitrogen pentaoxide. The second, dinitrogen tetraoxide. Now, do you see these two vowels that are adjacent to one another here? It's A and O. And again, here. Well, scientists really don't like when those two vowels are side by side, or really when any two vowels are side by side in the naming process. The reason being, they find that the name has a bit of a roadblock when being said out loud when you have those two vowels side by side. And so they've devised this process where you drop the vowel at the end of a prefix to really add some fluidity to the name when being said out loud. And so for the first example, if I drop the A at the end of penta, I now call the compound dinitrogen pentoxide. Now pentoxide relative to pentaoxide, right? And for the second example, if I remove the A at the end of tetra, I now have dinitrogen tetroxide rather than tetraoxide. So it does add some fluidity, but it is an odd restriction. However, it's a very, very important restriction to take note of, because if you do not drop the vowel at the end of the prefix, in fact, the name that you've written is incorrect. It is considered to be wrong. And so if you were to write dinitrogen pentaoxide instead of pentoxide, you wouldn't get the mark for that particular name. So although it is odd, you must keep in mind this one restriction. Remember though, the I at the end of di and tri are never dropped. This restriction only applies to A or O at the end of a prefix. Okay, so on this slide, I've provided some practice questions, and of course, as always, I've given you the answers to those practice questions within the slide. Again, I strongly recommend that you try your hand at these questions before you look at the answers, and only use the answers as reference to make sure that you're doing these questions correctly. Now actually, when it comes to writing out the chemical formula from the names of covalent compounds, it's quite an easy process. There are 3 steps. The first step is to identify the metal and the nonmetal. Now, of course, with these types of covalent compounds, they're both nonmetal. Now, the second step is to write out the chemical symbols. So we have carbon, which is C, and oxygen, which is O. And the third step, for each prefix, write its corresponding number after its symbol. And so because I have a di in front of oxide, I know I have 2 oxygen. And so this compound is CO2, carbon dioxide. The other example I have here is the compound dinitrogen tetrafluoride. Okay, so let's write the chemical formula. The first step is to identify any metals or nonmetals. And so, of course, I know that this compound is composed of 2 nonmetals. Now, it's very important to do this step to ensure that you're writing the chemical formula for a covalent compound rather than an ionic compound. Now, I know this name clearly is covalent because it has 2 Greek prefixes within it, but sometimes it's not so cut and dry. It's not so clear. And so by doing this step and ensuring that you have 2 nonmetals, or you have a metal and a nonmetal with a difference of electronegativity less than 1.7, you can proceed with confidence writing the chemical formula for that compound. The second step is to write the chemical symbols. And so, first is nitrogen, and the second is fluorine. And the last step, for each prefix, write its corresponding number after its symbol. And so di for nitrogen indicates that I have 2 nitrogen, and tetra indicates that I have 4 fluorine, giving me the chemical formula N2F4, dinitrogen tetrafluoride. Here are some practice questions, And as always, I've given you the answers to these questions within the slide. I strongly recommend you try your hand at these questions first before you look at these answers. These answers should only be used as reference to make sure that you're doing these questions correctly. And with this slide, I conclude this lecture and this package. I hope you understood everything I discussed today. Thank you for listening. All the best.